All right, everybody. So here's our first try at the online teaching. Here's the model that we're going to follow as we're going along. I'll send these out between 2 and 3 times a week. Should have a short video going over a topic or two. Each one of the videos will have a couple of questions at the end that you'll need to work out and you'll need to send back to me. You can scan those if you want to and email them. You can take photos with your phone and email those to me. However you want to deal with it, it's fine with me. This will be the format that we'll follow for the rest of the lectures. All right, we'll start back since it's been some time since we've talked about this again. Just to mention electron counting again. There's some good examples in the slides here from some classical important inorganic and organometallic compounds. So I'll just remind you again, I've taught the whole time the ionic method of counting. These slides also follow that ionic method of counting. And so if you want to count them the other way, it's fine with me with the neutral method. But this is a method I'll continue to follow here. And I'll just go into detail here with this first complex. We can see that we start out with our complex here and we first need to figure out what the charge is on the metal. Go down to the bottom part of the slide here. That means correctly assigning the charges to all of the ligands. The carbon monoxide here is neutral. The other carbon monoxide is neutral. The phosphorus here has 3 bonds, one to this big group, one to phenyl, one to phenyl. So it's just like an amine. So the phosphorus is neutral. This phosphorus is neutral. And H here is H minus. It's a hydride. It's not a hydrogen atom or it's not an H plus. It's a hydride because it's attached to a metal. And so we got H minus up here. The whole complex is neutral, and so it must be rhodium plus 1. Once we've sorted that out, we would go over to our periodic table. We would see that rhodium neutral would be 9 electrons. So if we remove 1 electron from that, we get that rhodium 1 is a D8 complex. All right, now we're ready to do the electron count for the whole complex. The metal, we just figured out, contributes 8 electrons. The ligand, we get 2 from the hydride, 2 from this CO, 2 from that CO, 2 from this phosphorus, 2 from that phosphorus. So we get 2, 4, 6, 8, 10 from the ligands. We get 8 from the metal. So this is an 18 electron complex. Well, especially since you'll be doing these things at home, it's not necessary that you memorize all of these things, but it's going to be good for you to go through and make sure that all of these make sense to you. And remember that the formal charge will matter because that will change how you count the charge on the metal, and also the number of electrons that are donated will affect the total electron count on the complex. All right, here's a little bit more review. We had talked about hapticity, where this X tells us how many contiguous atoms are connected to the metal center. And so right here, we've got this peroxo group. Just the 1 oxygen of this peroxo group is attached to the vanadium, so that's an eta-1 alkyl peroxo. And then over here, we've got this oxygen and that oxygen right next door attached to the metal center. And so this is an eta-2 alkyl peroxo. We also talked about previously this mu group, and only one of the ligands in this iron dimer down here is a mu. It's this oxygen atom because the oxygen is attached to the iron on the left and also the iron on the right. So it's bridging. It's a mu hydroxo that we have. Oh, excuse me, mu oxo that we have. I won't go through these in detail. I won't ask you anything that's this complicated, but it would be good for you to go through and make sure that all of these make sense to you. This first one here, again, real simple. It has got a chloride on it. The chloride has a -1 charge. All the other ligands are neutral, so that means we got rhodium 1 again. and then the ligands contribute 2, 4, 6, 8, and so 8 and 8 gives us 16. So this is a 16 electron square planar complex. You should go through and do this for yourself for these others. Just make sure that it makes sense to you which ones are charged and which ones are neutral. We talked about a lot of these. So these are all unsaturated ligands. That means they have either a double or triple bond somewhere in the ligand. And again, we're going to use that eta notation to distinguish different things. So we could have just a simple one bond to this. We have this eta 1 aryl that's here. Alkenyl would be a case where we've got a single bond here to this carbon, and we've got a double bond that's over there. So all of these have some degree of double bonds or triple bonds that are in them. Wouldn't worry about this too much. We've talked about this quite a bit. Just want to remind you, again, when we got something with a high eta count, like this eta 6 arene that's here, it could slip to be eta 4 and donate only 4 electrons, or it could slip to be eta 2 and donate only 2 electrons. You'll also notice that it follows our pattern here again. When we have an even number of electrons, the ligand is neutral, and when we have an odd number of electrons, the ligand is going to have a -1 charge. Just more practice for you. Like I said, the things that I ask you about won't be this complicated, or I definitely won't ask you just from a name to figure out the charge on these things, but it would be good practice to go through and make sure that this makes sense to you. More of that electron counting. All right, and we're finally getting to some of the new stuff. We talked about this just a bit, but I wanted to go through it again since it's been so long and we've had so many crazy things going on. I wanted to go through these again. So these are going to be the fundamental small steps that we'll put together very soon into a catalytic reaction. So you're going to look back at this. I'll talk about this in detail. Association of Lewis acids, association of Lewis bases, oxidative addition reaction, and ligand insertion reactions. This will make more sense after we've talked about each type. You can look back in the slide later. All right, well, we got two types of ligands that we need to talk about. So most of the ligands that are in your complex are going to be these spectator ligands. They're just sitting there. They're not doing anything really except keeping your complex soluble. So maybe you're doing this in an organic solvent and you need those ligands on there so it'll be soluble in the organic solvent, keeping it stable, and also making it more electron rich or more electron poor, whatever it is that you need it to be for your transformation. Where the real action happens is with the actor ligands. Those are the ones that are actually doing some chemistry. So we may have two actor ligands that are forming a CC bond or a CN bond. They're getting cleaved, they're getting put together. So most of your complex is going to be the supporting actors, the spectators. The actor ligands are doing the real business of the complex. All right, association of Lewis acids. We won't talk about these a whole lot. These aren't important for any of the catalytic reactions that I'll talk about, but this is a type, and you should recognize what's happening here. And this is a really weird type. Here we have a relatively electron-rich metal center, and then this BF3, you'll remember, it is a Lewis acid. It accepts electrons. We've got an electron-rich metal. And so we got this weird bonding here where it's bonding sort of backwards. It's a pair of electrons on the metal donating out to the ligand. Metal complex is acting as a base. It has an extra pair of electrons. And the BF3 is acting as a Lewis acid. This, what we formed here, we can call a Lewis acid, Lewis base adduct. All right, here's something that's going to be more common. I'll do this fast. We've talked about this one a bunch of times. So this is a D8 metal, so 8 electrons from here. We've got 8 electrons from our 4 COs. So this is just a 16 electron complex. We'd have to prepare this in some way. So that's sitting there with just 16 electrons, really reactive, and it immediately associates this extra pair of electrons that we've added in the form of this ligand to form this 18 electron complex at the end. So our metal, this is more standard, our metal is acting as a Lewis acid, the ligand is acting as a Lewis base, and we're forming a Lewis acid, Lewis base adduct here. Oxidative addition. All right, now the fun begins. we have a metal complex, we have this XY, this generic species here, and what happens is the metal inserts or injects two of its electrons into the bond, and we cleave the bond. Simple one to think about would be something like Cl2, so we have a Cl and a Cl here. When we inject two electrons, now we have Cl minus and Cl minus over here. But to do that, we had to take two electrons from the metal center. So the metal center charge increases by 2 units, and the ligand, which was neutral, becomes a -1 and -1 to give us overall a 2- charge. A really famous complex here is this Vasquez complex, and it does all sorts of interesting chemistry. Here we're looking at it to activate hydrogen. Hydrogen-hydrogen bond's extremely strong, but Vasquez complex can manage to activate it. So in doing so, check out what happens. We've got iridium 1, we've got H2, and over here we've got iridium 3. So H2 had 2 electrons. Now we've got 2 hydride ligands instead. So this hydrogen has 2 electrons, this hydrogen has 2 electrons, so this is a hydride, this is a hydride, and this is now iridium 3. Okay, so this is an oxidative addition. We've increased the oxidation number on the metal. The reverse reaction can happen here, where we go the other direction. Sometimes these are fully reversible, where we take a hydride and a hydride on the metal, and so the iridium 3 goes now and goes back and becomes iridium 1, and we eject H2. We can have actually two types, and this was confusing to folks for a while. I wouldn't worry about this too much, but this could be interesting to some of you. So we've got Vasquez complex. We just looked at this. We have a concerted oxidative addition reaction. So what happens is H2 comes in, gets cleaved. It always ends up with cis addition when we have this happen. This was confusing to them at the time, though. They saw if they added methyl iodide, they got the methyl and the iodide trans to each other. So overall, they were confused because we see iridium 1 go to iridium 3. We get an oxidation of the metal center, but we end up with this trans arrangement. This was finally assigned as an SN2 type displacement. So this electron-rich iridium 1 acts as nucleophile, attacks methyl, ejects iodide, and then this iodide comes and associates later. These are not always reversible, so this reversible arrow meaning that that this would be something like 50-50. It's not always the case. It usually will lie in one direction or another. For example, if we've got something here like Rx, so we might have, I don't know, again, maybe methyl iodide, and it goes over here to have X minus and R minus, and this would lie really far to the right-hand side. But this other one, we've got R with H, and we can do this reaction, but you'll notice the equilibrium in this case, for most metals, lies really far to the left-hand side. So it's doing this just a little bit, it's doing the oxidative addition just a little bit, or you could say the reductive elimination is favored. Here the oxidative addition is favored. All right, really important type of reaction that we have here. This is an insertion reaction. And initially, they were termed this because we've got carbon monoxide here, we've got a metal carbon bond here. Initially, they thought that the free carbon monoxide just came and clipped into the bond, and we got this insertion reaction. On the next slide, we'll see that it's more complicated than that. But regardless of how the mechanism works, the exciting thing here for any organic chemist is we've formed a new CC bond. And any time that we can form a new carbon-carbon bond, it's a big deal. This reaction can be called a carbon monoxide insertion reaction, or it can be called a migratory insertion, and that's actually a better name for it. All right, so here's what happens overall. So they were able to find, using C13 labeled CO, right away that it's not the extra CO that we add in that ends up here in the attached to the carbon, but it's one of the ones that was already on the metal center, and that was always the case. Okay, and so it ends up that the mechanism for this is that the methyl group just kind of does an internal attack on the CO. So this methyl carbon, the C minus, attacks the CO, and we get this acyl group. And then the CO that we've introduced, the CO gas, comes in and just takes the site on the metal center that we have generated by doing the insertion reaction. And this is also promoted by bulky ligands in the initial complex. And the reason for that is if we have bulky ligands around here, there's some strain that's relieved when we do this insertion reaction, because we went from 6 coordinate in the starting material to 5 coordinate in the intermediate. Because we've taken 2 ligands, a methyl and a CO, and made an acyl group out of it. We've decreased the steric congestion around the metal. All right, finally, and we'll just kind of preview this one, insertion and deinsertion reactions. Another type of reaction that can go is we take a metal and we bind an alkene, cis to a hydride, and this inserts in, and we had at first here a metal hydrogen bond, and we had an alkene sitting right next door to it. Now we have a new metal carbon bond, and the hydride that we started with is now out here far away from the metal. This is a key step in catalytic isomerization and hydrogenation of alkenes, also important for the decomposition of metal alkyls. And this is the first step in starting a polymerization. So if we wanted to make polyethylene, this would be the first insertion. And then starting with this complex, we can actually add more alkene in and do subsequent insertions. All right, so here's how the homework's going to work. There's not going to be the big problem sets. It's going to be simpler for us just to have basically homework a couple times a week, and it will be at the end of the slides like this. The first thing I'll ask you to do is to draw out the detailed mechanism for the reaction between our complex here with triphenylphosphine to yield this complex. And then finally, this will be on the next slide, give the electron counts for each of the organometallic complexes in the catalytic cycle for Wilkinson's catalyst, which is given here on the next slide. So I want you to just print this out and write the electron count for the metal and for each of the ligands in here, 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 and there, just so you'll see how that progresses. Most of these are going to follow the kind of patterns that we've already talked about in class. Signing off.